Gilde sir, am I audible to you?
Yeah, good evening, ma'am. Good evening, sir.
Good evening. Yes, good evening, sir. Good evening. All the participants are informed that our next resource person have already joined the session, so we'll directly start this session. So after the understanding of micro level policies and frameworks, it's time to focus on the technical innovations that make the sustainability goals achievable. Our final and concluding session of the FDP is on case studies of simplified computational approach for solar thermal applications. It is to be delivered by Dr. Ravindra Gilte, Associate Professor at the Energy Center, Maulana Azad National Institute of Technology, Bhopal. As on day one, Dr. Siddharth Undirwadi sir said, Dr. Ravindra Gilte is the opening and closing batsman of this FDP. So, Dr. Gilte, I, on the behalf of PS College of Engineering, Chhatrapati Sambhajinagar and organizing team, warmly welcoming you for this session. So, I will deliver this session for your expert talk. Sir, over to you.
Thank you, ma'am. Thank you, Kakade sir.
Yes. Want to give some instruction to participate, just 30 seconds. All the participants are instructed that your online test will be conducted from 6:30 to 7:30, followed by the valedictory program. So all are requested to continue for online test and valedictory program too. Sir, over to you.
So, very good evening to all the dear participants for joining this session. As the ma'am has introduced the topic of the discussion for this today's FDP, it is about the case studies of a simplified computational approach for solar thermal applications. The idea keeping this topic is very different than the very first topic. Here, we wanted to understand there are so many solar thermal applications are there, and with a simple understanding of the concept, we can proceed with our research, we can proceed with our work, and based on the software which is available, like the ANSYS software is also available, CFD software is available, we can try to complete our research through the simulation. And by way of assuming or by way of the treating the problem, complex problem into a simpler problem, we can generate the results that is can be publishable in a reputed journal. That is basic aim. So here, the topic of the discussion will be like this. We'll try to introduce and we'll try to understand majorly the four parts of the solar thermal applications. Although there are so many applications are there, in the first part, we'll try to understand how we can design and simulate, obtain results on a cavity research of a parabolic concentrator. In a second part, we'll try to understand the again the design consideration, design assumptions, and the procedures to obtain results on receiver of a CLFR. Now, what is this CLFR? What is this? The third parameter called as PTC. We'll try to understand. Those who are earlier taught this course of solar energy, they will be knowing these terms. But for the general audience, I will try to briefly introduce these terms also. So third part will be on a absorber tube of a PTC. And last but not the least, we'll try to understand how the emerging areas which all the Europes and all the abroad countries they are researching on developing the thermochemical solar reactors. So if I start with the first concept, why all these kind of technologies are available. So here it is the concept that energy is the fundamental input and essential need for the advancement, modernization, and economic evolution of any nation. So the question is how to achieve the future or current thermal energy requirements for meeting the energy demand. And one way of this is going for a solar way. So if you look at what kind of the applications we are targeting, in industries, there are so many range of the temperatures. Like if you look at the low temperature heat requirements for the boiling and so many purposes, which is listed over here, it almost 30% of the requirement comes for the below 150 degrees Celsius. Then medium temperature heat application is also there up to 22%. High temperature applications above 400 degrees Celsius are required for material transformation processes. So these are the current range of temperature. And then if you look at the kind of systems or kind of techniques or technologies we are using to propose or to provide this kind of temperature range, this is the thermal requirements of the industry. So almost 45% we are consuming coal, 30% we are consuming natural gas, 15% oil is there, and the 9% renewable is there. Now it's time to let us try to as earliest as to replace this heat requirements from the renewable. That is the basic aim. So if I look at the types of the concentrators which we are also discussing, so here there is a classifications are available like non-concentrating collectors and the concentrating collectors. In non-concentrating, we have the flat plate, compound parabolic collectors, the evacuated collectors, the parabolic trough collectors. So in our sessions, as I mentioned, we'll be discussing on a parabolic trough collector. We'll be discussing on the computational approach for the parabolic dish reflector, and then also the linear Fresnel reflector also, that is we call it as CLFR. These are the temperature range and these are the concentration ratio. So as on the basic, the definition of the concentration ratio is that suppose say if you have the parabolic dish is available. So this is the area available where the solar radiation can be incident, let us say. And if you make this as a reflector or reflectant kind of material, and if you try to concentrate all this radiation back to the smaller area, then we have the two types of the areas are available. One area which we call it as a aperture area, which will be very very bigger, like this is the aperture area. And we also have the smaller area onto which all the radiation will be concentrated. So if I try to divide this receiver area to the aperture area, so suppose that this area is 100 times bigger than this small area, then the concentration ratio will be around 100. So if I go more and more towards concentration ratio, I can achieve the temperature of even the 2000 degrees Celsius. So this is the way of going for the higher and higher temperature by simply increasing the concentration ratio. So I will try to not too much devote our time on this technologies. Uh, as I said, again I will recall, if you have taught this solar energy courses in your institutes, you may be familiar with these terms. We'll try to understand the conceptual things, how we can simplify the computational methods for initializing our examples or the case studies. That is the basic aim. But let us look at, since this will be also discussed, so this is called as parabolic trough collector. We call this as a PTC. So in a PTC, if you look at over there, the rays are allowed to incident on the reflected surface, parabolic trough, and then it will be concentrated in a linear focus, that is line focus is there. So this we call it as a line focus kind of technologies. Here it is the parabolic dish collector where all the rays will be concentrated on this focal point. So as I mentioned, concentration ratio of this will be much, much higher than parabolic trough collectors. Then there is a third concept is there, linear Fresnel reflector. So all the reflection, that is all the incoming solar radiation will be allowed to reflect on this bottom of this receiver tube or the observer tube. So we have the all these reflecting surface that will be lying on a ground, and receiving surface will be available. Again, the line focus is obtained in this case. So there is a two types of terminology. One is called as the line focus kind of concentrator. Here it is the line focus. This one is called as the point focus kind of technology, and this will also be called as the point focus kind of technology. So in a typical solar thermal power plants, we can utilize this kind of the technology. So all the radiation will be falling. Now, in our case, we'll be discussing the computational of this type, and this type. Let us begin with the case studies. So let us say this is the first part, cavity receivers of the paraboloid concentrator. So as I mentioned, this term or this big dish is called as the parabolic dish reflector. So in examples we have taken, this portion, this cylindrical portion is called as cavity receiver. So this is our example where we'll be focusing and we'll try to generate the results. So this is called as our cavity receiver. So here this system is used for supplying the industrial process heat at intermediate temperature and high temperature range, available at Mahananda Dairy, Latur, Maharashtra, India. So what kind of opportunities are available to start with analyzing the situations and generating the results? We can analyze the cavity receiver. But if you look at over here, it appears to be a complex kind of situations is there. So this is the parameters which can be investigated. Like this cavity receiver is made up of the helical coils, and then there are two options are there. Since this helical coil, or sorry, this cavity receiver is open from the one end, there will be a losses. So if you look at the convective and radiative losses will occur through the air, which can enter and which can take up the heat. Then whatever the kind of installations we provide to the surrounding of this cavity receiver, there will be a conductive losses. So our parameter of investigation will be how to design a cavity receiver that can yield or that can minimize the quantity of convective and radiative losses, because conductive losses more or less can be controlled by the insulation, but the convective and radiative losses, it all depends on the type of the cavity receiver and their shapes and our understanding how to minimize it. So again, these are the parameters. Since if you look at over there, now this entire dish will be subjected to the sun tracking. Now, if it is subjected to sun tracking, the position of the cavity receiver will not be a fixed position. For example, if I take the, like the sun is here during the morning time, so rays will be here. So I can orient the dish in this way. So cavity receiver will be here. So rays will be going this way and it will be reflected inside. Rays will be incident and then reflected inside. So orientation is horizontal during the morning time. If I take the sun during the afternoon time, orate, then the dish can be kept like this and the cavity receiver will be in this position. So your rays will be incident on this surface and then it will be reflected towards the cavity receiver. Again, rays can be allowed to incident on the reflected surface and it will be entering over here. So the position of the cavity receiver changes throughout the day, like from the morning time, afternoon time, and again in the evening time. So in our understanding or in our computational work, how to take care of this inclination of the cavity receiver which is happening there. So we have decided to include the one of the parameter, since the losses are depends on the angle of inclination of the receiver. It also depends on the how much is the temperature of this wall and the temperature of the atmospheric air. It also depends on the wind speed, because here, as I mentioned, since this kind of if you look at the size of the dish, if I take this as around a 6 feet is there, so you can just try to understand the the size of the receiver as well as the size of the entire systems. So the wind which is will be prevalent at that place, we cannot uh, avoid to interrupt this kind of situation. So since it will enhance the losses, convective losses will be get enhanced if the wind is there. So that effect can be also be studied through the simulation. Now, since our topic is about the computational approach, simplified computational approach, we'll try to make it use of the NCCFD to simulate this. So aperture diameter, which is this can be the aperture diameter, and the length by diameter can be the aspect ratio. So now the scope, what kind of parameters like here, if the temperature of this surfaces or temperature inside the cavity receiver, if it increases, which is good for us, but at the same time, heat losses will also try to increase, and as a result, the performance will try to deteriorate. So what are the scope is there? We can compare different types of the open cavities of different shapes, sizes, and then we can compare under no wind conditions and the windy conditions to identify the best shape having the least losses. We can also try to propose the generalized correlations for predicting the heat losses from the open cavities of different shapes operating isothermally. If you have attended, if you are dealing with the course called as the heat transfer, then in that course, many times we refer the Nusselt number correlations or the other correlations. Similar kind of correlations can also be generated for this specialized case or for the customized case of ours. So now the options available when you try to carry out the numerical simulation. Now this receiver is open to the atmosphere. So very first thing is what we have to consider. We have to approximately take one area which will be representing the atmosphere. So if I take this, I cannot only take the cavity, or I cannot take only this portion. I should also account for the atmosphere. So what is the best solution? Best solution is that you try to take either cylindrical enclosure or you can take the rectangular enclosure. It doesn't matter. What is matter is what is the size of this enclosure with respect to the this. If I take, let us say if I take the almost 20 times larger, that is if this larger enclosure is 20 times larger than this cavity receiver, then the condition will be as good as the atmosphere. So this is the very first simplifications we have to consider over there. And the basic idea is that, suppose say why we have taken this consideration. The reason is that because this presence of this hot cavity will be affected adjoining air to a certain extent. Let us say the air which is present at a, let us say 1 meter apart from this receiver will not get affected. So same concept we have utilized over here, and we have simplified the concept that if I take the three-dimensional simulation, this thing will be there. If I take the two-dimensional simulation, then you can place the cavity over here. This is the cavity. And again, as I mentioned, the dimensions can be 20 times or 30 times, whichever. So this can also be subjected to your investigation, that how much is the size is required, or you can also refer to the published literature to understand what other people have done or something. Then the in actual scenario, there is a bit difference is there as far as the boundary conditions that we try to adapt during the simulation. Like here, very first assumption what you are making is your outer surface which is insulated is not losing any kind of heat by conduction. So we are trying to provide the outer surface with a adiabatic boundary condition, and then the inner surfaces of the cylindrical cavity we assume to be at a same temperature. So the boundary conditions which we'll be utilizing is the isothermal. So we can assume the temperature of 523 Kelvin for one investigation. We can increase to 923 for the second investigations. And here more important is, since your boundary will be available, so you can put the cylindrical enclosure surface, the entire cylindrical enclosure surface under pressure inlet condition. So these are the few of the boundary conditions used in the present numerical scheme. Then now the question that can be come to our mind is that, since our cavity receiver is sometimes horizontal, sometimes vertical, sometimes in an inclined position, if I try to model these things, if I try to model, suppose if I try to model, what I will do, I will simply try to make one enclosure, that is larger cylinder. Then I will try to include the another cylinder of this shape, but it will try to simulate the conditions of only the when the cavity is horizontal. With the same modeling, is it possible to obtain a result as good as the cavity is now in a vertical direction or vertically downward facing? It is possible in simulation, but the values of the gravity, CFD or the simulation provide the values of the gravity 2D or in a 3D, then we'll have to provide, if it is the horizontal is there, then one, it is absolutely there. And if I model it in a horizontal way, but now I want to obtain results in a inclined cavity, and y component and the z component of this gravity, and put it there. So what is the benefit I obtained over there? I obtained the benefit of modeling the example or modeling the situation only once and investigating the uh, uh, yeah. So here it is the case of a meshed system, and we are discussing on the size of the mesh which we can increase inside some inside the cavity receiver to trap the physics which is happening over there, and atmospheric enclosure which you have created on the model, it can make with a coarser mesh. So there is a combination of the fine mesh and the coarser mesh to avoid, or what you can say, to reduce the computational time. So types of the cavities can be investigated like, here we are discussing on the different boundary conditions that can be taken. So here we are assume the no slip boundary conditions as at a one, and fluids are taken as a incompressible and Newtonian fluids, as mentioned, incompressible and Newtonian. Since that we can assume at a constant temperature, that is uniform constant temperature, and therefore the isothermal boundary conditions can be given for the absorbed tube. Then the glass cover subjected to the convective and radiation losses from the outside as well as from the inside. So accordingly, we can assume the different values of a heat transfer, that is convection coefficient, different values for the inner side, and convective transfer coefficient, different values for the outer side. The different values of the emissivity of the top wall, bottom wall can also be assumed. The external emissivity of the bottom mass and the heat transfer coefficient, as I mentioned, can be assumed in the range of 5 to 25. The tube surface temperature can be in the range of 350 to 550 Kelvin. If I do this modeling, then we can obtain the complete physics, what is happening inside. So if you look at, since the air gets trapped inside the cavity receiver, we can obtain, or we can visualize, there is a zone of stagnant air which is in and around the tubes. So this will also get varied if I change the temperature from 350 Kelvin to the 550 Kelvin. Then in the second attempt, we can uh, change the orientations of the receiver tubes. So you can make it as a staggered kind of arrangements over there. And this investigation can be obtained for the 2D also, as well as for the 3D also. So if you want to visualize this effects or likewise effects, we can only go for the 2D simulation. And if you want to visualize the effect of what is happening through the working fluid, which is entered at one end and exited from the other end, then we can go for the three-dimensional. So it all depends on the what kind of the findings we want to generate through the simulations. So 2D generation and 3D generation, we have to first decide the parameters, and then that parameters will help us in simulating 2D or 3D. So likewise, like this is the symmetrical case is there. So as I mentioned, we can obtain isotherms, we can obtain streamlines of different temperatures. So this can be extracted through the CFD with the different values of the heat transfer coefficient on a bottom of the cavity receiver, that is the glass. If it is 5 watt per meter square Kelvin, that is the air which is available in atmosphere is not so strong. But if you go for the stronger wind available, so we can obtain H is 25 watt per meter square Kelvin. Then if you look at the third part, that is the parabolic absorber tube of a parabolic trough collector. So we will be targeting our design and simulation for receiver tube of a parabolic trough concentrator. The previous example was about this, simulating either a portion of this CLFR or in a 2D as well as in a 3D format. So these are the few of the findings are available. There are so many studies are available where the people have taken inside, like for example, this is a tube is there. So this tube will be a cylindrical. At one end, will be allowed to pass the water or any of the working fluid, and it will be allowed to take it from the other side. So inside, we want to enhance the heat transfer. So we'll have the different options of enhancing, breaking the thermal boundary layer. So these are the different options. Like we can go by the twisted tape, we can go by the porous inserts. So inserts and surface modifications can be possible. And then we have the options of investigating by using the water, by using the alumina, by using the nanofluids. So many investigations are available in the literature. So what will be the novelty in this case? How we can take this as a research or take this as a our work? We have the options of providing or suggesting or coming up with the any of the novel kind of arrangements over here. This is a typical case. Uh, we can simulate by providing the heat flux conditions. Now, if you look at the simplifications, what is happening over here, if I try to draw this in this fashion, and this is the tube is there. So here the radiation will try to strike only on this portion, or radiation at the most will try to strike only on this portion. So on this bottom surface of the receiver, that is if I try to draw this as a cylindrical surface, this portion will receive the concentrated radiation. So these are the concentrated radiation, and top portion will receive the radiation of a normal solar radiation. So for example, if the solar radiation in this situation is 800 watt per meter square, so up to from here to here, the boundary condition will be subjected to a flux of 800 watt per meter square. Now, earlier we have mentioned that concentration ratio can be in the range of, let us say, 20. If the concentration ratio is 20, then whatever the flux that is incident on the bottom surface, that is from here to here, I have to multiply 20 into 800. So this much will be the solar flux I should assume during the boundary conditions. So here it is the mention over here. We can have the heat flux boundary conditions, but there are two types of the boundary conditions over there. Then we can enter the fluid at any inlet temperature. Let us say 300 is the temperature, and then we can also need to incorporate the materials over there, like the absorber tube is made up of the either the steel is there or the copper is there. But normally, considering the length of the absorber tubes, we go by the steel. Then the pressure outlet conditions we need to mention over there on the other side. Then as I mentioned, if this is the DNI, that is 800 watt per meter square on the top side, then here it is the concentrated times of DNI, that is just I mentioned 800 into 20. Significant length is required to find out to visualize the changes in the temperature. So the temperature length of the receiver can be in the range of 7.8 meter, and then it depends. We can assume the glass surface over there, because if you look at there out, this is can be considered one tube surrounded by another concentric glass cover. So while simulation, we may avoid the presence of glass at one attempt and try to simulate and generate the results. In the second attempt, we can use this glass envelope, but the properties of the glass will be required to feed it into the modeling and simulation. So both the approaches are possible, but it all depends on the types of the boundary conditions which are putting over there and trying to generate the results. So here, if you look at, as I mentioned, different studies are available. So if you can come up with your own modification, like for example, we have come up with the one modifications which you have mentioned over here, that is the convex concave receiver tube, a double corrugated. So we have carried out this changes, and then we can claim it as a novel kind of arrangement is there, and the results are possible to get it published. So we can take the cross sections at a different length, and we can visualize from the inlet to the at a distance of 2 meters what is happening there. So we can take the cross sections and we can find out the qualitative what is happened to the working fluid. So let us say from the inlet to the outlet, we can obtain the temperature that is get developed, the temperature of the fluid that is get developed also. So all this are possible. We can also try to yield the values of the velocity variation. And if you look at over here, we can in fact try to obtain results by incorporating the pitch inside, like corrugations are provided. So these corrugations will be denoted by the pitch also. So by varying the different pitch dimensions, we can obtain different results. So these are the two. Then if you look at the now the last part of this presentation, the last technology which I'm trying to put across this FDP is the solar thermal applications which are shown so far is available from the decades. So we'll try to take the another example or another applications which also the research is happening abroad, and many of the universities and the researchers, they have undertaken this. So this is about the generation of the hydrogen through the solar route. So why we should bother about generation of the hydrogen? So generation of the hydrogen is not only for the hydrogen car. We treat it as a hydrogen as a energy carrier. So how it is possible? If you look at the case over here, presently the generation of the hydrogen as such is taking place. Coal contributes 71.27%. The natural gas contributes 27.26%, and generation of the hydrogen by renewable is hardly 0.73 or 0.74 is there something. So very less contribution of hydrogen is there. Now very question that comes to our mind is that what is the uses of the hydrogen? Why we should try to generate the hydrogen through solar route, and is it possible to simulate the similar kind of situation? So here it is, the list is available. Like the industry required the hydrogen for ammonia, for oil refineries, for methanol production, and for the other purposes. Here it is, the share is available. Like 61% of the hydrogen is required for the ammonia production. And since we wanted to get rid of this fossil fuel based of generation of the hydrogen, the solar is the best way of generating the hydrogen. But there are challenges are there. Like here, the pathway is one is the renewable sources, like we can go by the biomass and we can generate the hydrogen. The second one is the water is available, like here the H2O is available. If you can split, if you can split this water into H2, we can generate the hydrogen. But for splitting of the water, we require heat. That heat will be supplied through the solar way. So if three pathways are there for producing the hydrogen with the solar energy. There is still some issues with the network connections. So here it is the case. We have the three options: electrochemical pathway, photochemical pathway, and thermochemical pathway. We'll try to discuss on a thermochemical pathway of generating the hydrogen. And for us, the concentrated solar radiation is the one of the options for providing high temperature required for water splitting. So the process is endothermic. As I mentioned, it requires the heat, and that can be supplied through the concentrated solar radiation. So these are the long-term kind of visions are there for utilizing the solar thermochemical hydrogen generation. So the next few slides we will try to discuss on a hydrogen production using modified solar reactor from two-stage water splitting CO2 based thermochemical cycle. So let us first try to categorize the three types of the hydrogens are available. One is called as the gray hydrogen, which we are producing from the natural gas, but it is emitting a CO2. Second one is called as the blue hydrogen, wherein you can generate the hydrogen from the natural gas, but there will be a generation of the CO2, but we can compensate and we can keep it underground, or carbon capture can be possible and store it somewhere in the beneath the sea. So that we can call it a blue hydrogen. But we are proposing a third type, which is called as purely the green hydrogen, where the electricity which is required for splitting the water will be taken from the solar. So solar is the pathway available, and then as such, whatever the hydrogen we can produce, that is called as the green hydrogen. This is the pathway. So this is a requirement, as I mentioned, for a different from the different industry. Then we why we I mean one uses of the hydrogen is for the hydrogen economy. The second use is for the hydrogen car kind of situation, and third one is production of the solar fuel. Let me first try to introduce here what is meaning of the solar fuels. For example, if you take the case of the diesel over here, so the deflation of the diesel is which is happening there. Now the question comes: can we generate the diesel in a lab? We call this as a synthetic diesel. Or the second example, let us say the kerosene is available, or you can take the case of the jet fuel. So can we generate the kerosene? Can we generate the jet fuel? Can we generate the petrol? Or can we generate the diesel in a lab? It is possible to generate all these fuels. We call it as a synthetic fuels. And in a broader way, we call it as a solar fuels, because we are trying to utilize the solar pathway. So here it is there, solar to hydrogen. So this is the one concept over there. We can visualize utilizing the solar concentrator, and we can visualize there will be some kind of arrangements wherein the water will be allowed to inlet. Some kind of reactions will try to initialize over here, which will help us in separating the hydrogen and the oxygen. It looks very simple over here, but when we try to model and when we try to incorporate in our simulation, let us look at the case. So case is like this. Okay, before we go for the case, the pathways are there. We are trying to adopt the solar thermochemical cycle. There are so many other options are available for generating the solar hydrogen. For a solar thermochemical cycles, there are so many solar thermochemical cycles are available. We can classify it as a volatile cycles and the non-volatile cycles. Non-volatile cycles are the redox based. So the cerium oxide, which we have mentioned over there, will belong to this category. So concentration already I discussed. This I will skip it. This I will skip it. Now, in the solar thermochemical processes, we have the solar thermochemical cycle. Inside, we have the metal oxide, and we have taken the non-volatile based metal oxides, which can be carried out by the ceria. So these are the pathways there. In a simulation, we have to utilize the ceria based reaction. So our idea, will try to provide the solar heat, try to initialize these reactions, but the temperature which is required is 4300 Kelvin. Now, if I use a single step, this is also called as the single step. If I use the single step of conversion, then it requires very high temperature of 4300 Kelvin. If I modify this case, and if I go by the second multi-stage, like two-stage over here, so there are so many cycles that are available, like in the range of 850 to 2200 Kelvin. There are more than 280 cycles are available. to convert the to split the water into the hydrogen, as I mentioned. So now this we have done. We have carried out the screening of the all the cycles available. We obtained that how many number of steps are required, what kind of chemical reactions that we need to uh, undertake during the simulations or during the modeling. And then we have obtained that if you try to adopt the two-step cycle, then the temperature can be in the range of 1000 degrees Celsius, which can be easily generated through the solar route. The complete chemical kinetics are required and to understand and to simulate this situation. But let us try to visualize. Uh, there are redox reaction is there. Now, if you look at the what is the meaning of the redox reactions, there are two pathways are there. In one pathway, we'll try to adopt the solar radiation to be fall on or to be incidents on the CvO2, and then there will be a liberation of the O2 as well as there will be formation of the CO2X is there. And then if you try to pass the steam, so here basically we are passing the steam over there, then we can generate the hydrogen. So these are the reactions of high temperature reduction and the low temperature oxidation. So since the reduction and oxidation occurs one after the other, we call it as a redox reaction. So here it is mention of the redox reactions. The temperature range available for the reduction reactions are different. Like in the reduction occurs in the range of 1500 to 600 degrees Celsius. So in the simulations, we have to provide this range, and in the second case, we have to carry out the reactions under a range of 800 degrees Celsius. So let us look at what kind of possibilities of research is possible, possibilities of work can be undertaken. We can investigate the flux distributions in the solar cavity. We can also investigate the thermal characterization, porosity analysis. We can investigate on uh, the CO2 based solar cavity receiver, their shapes on oxyfuel radiant heat source. And we can also carry out the performance evaluation. If you look at the approaches, the numerical simulations will be carried out. Before that, the flux distribution studies can be needed to be completed, and then the flux values need to be taken as an input for the simulation. I'll just try to directly jump to the category. Now, here it is the case. What you have done, we have taken one simple cavity receiver. We call it as a solar reactor. So this we call it as a solar reactor. In a solar reactor, we have provided one glass surface, quartz glass surface, and here we have provided the reticulated porous media is there, that is RPC. So RPC substance, we have kept it to a depth of 20 millimeter, and we have also provided one gap over there to pass the inlet of the gases, that is inert gas, and we have also provided the provisions for the outlet. Aim of the study which we try to carry out, we wanted to carry out what is the effect of flux distribution. So if the rays are incident on this through this cavity, what will be the flux distribution on this surface, that we wanted to first understand. So for the first study, we have kept the thickness as 20 millimeter, and then later on we have also investigated the effect of varying this thickness also, and varying this inlet positioning also, as well as varying of this the space for the inert gas flow. We adopted the this MCRT, means Monte Carlo rate racing. So it is basically the Monte Carlo rate racing techniques we have adapted to generate the flux distribution. Uh, I will not go much detail into the what is happening exactly into MCRT, but the basic idea is before we try to simulate in a CFD, we wanted to understand what is the solar flux. Now, the solar flux distribution we obtain through the Monte Carlo rate racing software called as SolTrace. So, SolTrace software is utilized to obtain a solar flux distribution. Here it is the case. We have taken the two different cases, like if the focal point is on the aperture, or in the focal point is 20 millimeters inside the cavity. Now this one is your parabolic dish is there, and this one is the cavity. So these are the parameters. Then in a radiation of model available in the ANSYS, we have the discrete ordinate model. So this is DO radiation model, or discrete ordinate model, was invoked to analyze the radiative losses. This one is obtained through the soul trace. So whatever the radiation that is falling on the parabolic dish can be reflected to generate the profile. Based on this profile, we obtained temperature, and this temperature value were validated with the available studies, and we obtained that through the simulations we can generate the solar flux distribution, which is acceptable within a variation. Therefore, this can be chosen for the further analysis. And then we have also considered the different the surface errors. Like for example, if we take this reflector will have the some kind of errors is there. So that effect of the error also we are introduced, and how it affects the solar flux distribution, that can be obtained through the simulation. And these are the results obtained. What is happening inside, if you visualize, temperature distribution can be obtained. Then we can also try to visualize what is happening, the effect of 2 mrad slope error to the 4 mrad slope error, how it affects temperature distribution in the radial direction. Then in the axial directions, how it get affected. Then the effect of the cavity length can also be what is happening, the temperature distribution inside the cavity from the inlet of the cavity to the depth of almost 120 millimeter of the cavity, how the temperature will get affected with a different slope error. This can be analyzed. And the temperature flux contours we can visualize over there. We can obtain results from there. Then if you like as I mentioned, there can be a different configuration, different kind of shapes that can be investigated, like cylindrical cavity can be clubbed with a second cavity, and we can modify the shape. And then similarly, the effect of its placement on a focal point, or the deviation from the focal point, can be discussed or can be obtained. So by considering the different kind of parameters, we can investigate and we can obtain different results. Then this is for the second aspects. If I try to present in terms of the contours, it will look like this. We can again try to analyze the situations of temperature profile in the radial directions, in the axial directions for the case 2, and again for the length. So all these things are possible when you try to extract the results from the simulation. Flux profiles can be obtained. Effect of optical errors, the effect of the velocity increments in meter per seconds can also be obtained. So basic idea is about first one is, if you want to generate the solar fuels, or if you want to generate the water splitting, so it is possible to simulate. What we require now is the chemical kinetics to be incorporated, how exactly the splitting of water happens over there. So that can also be considered over here. So here, if you look at, we have obtained the gap of 20 millimeter, then 25, then 25 millimeter. All these aspects can be studied. If you look at temperature contours are obtained, this aspect 3 is obtained. So here we try to incorporate the chemical kinetics. When you try to incorporate the chemical kinetics, there will be evaluation of the hydrogen and the oxygen. So when you try to measure the percentage of oxygen generation or the hydrogen generation, we can estimate the solar to fuel efficiency. So solar to efficiency also can be obtained through the research or through the investigation. and we can also investigate the different positioning, like here it is the vertical position, the positioning of the inert gas, how you provide the inert gas over there. The effect of that also can be investigated. And then orientation, as I just mentioned, if I try to keep it vertical 90-degree or 65-degree, accordingly the results will vary. These are the all the findings for the temperature distribution. This is what the reactions which we need to consider through the chemical kinetics, the temperature range. So as I mentioned, reduction and the oxidation, both the reactions need to be considered. This is what the kind of effect of thermal reduction temperatures on the equilibrium compositions. So now the discussion what we have mentioned is it also involves the understanding on the chemical engineering or chemical kinetics. So in NCs we have the options of so many models are available. Some deals with the thermal, some deals with the chemicals. So we need to understand, and if it is possible, try to make aware of this chemical kinetics models, and then try to practice on this chemical kinetics model. You'll find out that so many things can be done through the computation. The idea of presenting this result is that there are enormous opportunities are available to generate the result through the simulation. Now, just to share you that all these results we obtain through the simulation. We are not carried out any kind of experimentation because it is the beyond our scope. But just by simulating and just trying to carry out the simulation on a laptop, we can generate similar kind of results. So many things are there which we have done. So basic idea, just try to take any simple example, try to simplify as it is possible, and then try to go differ and differ into the topic.
Yes, sir.
Thank you.
Thank you, sir. Thank you so much.